Hello TVMCon. I'm Stephen Bomirski from the University of Washington, here to present our work on Fuzzing TVM Relay, which was done with my colleagues Edward Misback and Michael Flanders. As we incorporate new features into TVM, it is increasingly important to ensure the reliability of TVM to support users. The principal means for ensuring reliability is testing, but TVM currently has significantly less testing code than implementation code. While this is a very reductive measure, it may be an indication that we are not testing enough, particularly when we consider all the different possible usage scenarios and how complex features could interact. Unfortunately, writing test cases can be laborious, since test cases are entire relay programs and must be carefully constructed to trigger specific features. It may take some more discussion to settle on how to best improve TVM's testing, but this presentation explores how we could automate away some of the effort using automatic program generation, or fuzzing. In order to fuzz test a compiler, we must be able to generate input programs that are guaranteed to be valid. This way, if there are any errors with generated programs, we know that it is the compiler and not the generator that is at fault. In the case of Relay, we thankfully have the type system to serve as a means of checking that generated programs are valid. The rest of this talk will discuss how we can use Relay's typing rules to build up programs that are guaranteed to be well typed. As a proof of concept, my collaborators and I have implemented a prototype fuzzer in only about 2,000 lines of Python that can handle about 20 tensor operators and can support all parts of the language dealing with statically shaped tensors. In the following slides, I will explain how our prototype works. Most of Relay's type system is similar to those of well-studied functional programming languages and thus behaves quite nicely. For constructs that don't involve tensor shapes, all we have to do to generate programs is to follow typing rules in reverse. We pick a type, then we pick a construct that can have that type, and we can proceed recursively for any sub-expressions whose types usually follow easily from that of the final expression. Unfortunately, not every case is that simple. The type system's greatest strength, being able to reason about tensor shapes, adds a lot of complexity. Each operator has a relation that decides if the combination of argument shapes and the return shape is valid, which means that the shapes of the arguments can affect the shape of the results. Consider, for example, broadcasting. In order to generate valid programs, this knowledge must reside somewhere. And unfortunately, to make matters even more complicated, the Relay compiler itself checks relations using imperative procedures in C++, which are not formally specified and are difficult to reuse outside of the compiler. This poses quite a practical problem, but not an insurmountable one. Our prototype tests two separate approaches for solving type relations. The first approach is to formalize the relations in a solver domain, such as integer linear programming, and then when we build up a program recursively, we can set up solver constraints for a given return type and solve for argument types. This approach is surprisingly simple since it only requires one solver query at a time. Additionally, the queries themselves are composable and may be reusable in other solver-based tools down the line. However, using a solver requires us to independently reformulate each type relation, which is a lot of manual effort, so we also explored an alternative approach. Our other method of solving type relations was, in principle, more similar to the imperative checkers that TVM already uses. Namely, rather than starting with a return type and solving for argument types, we instead generate argument types and compute a return type when those are valid. Hence, we call this a stochastic approach. We keep all valid combinations in a solution cache, and then later during type generation we can fetch solutions from the cache and insert the relevant operators. In principle, this should allow us to recycle existing relation checkers without independent reformulations and even without a solver. And while this may be less flexible and less neat than using a solver, the advantages in simplicity may outweigh that. In the process of developing our prototype, we came across a number of bugs, which I summarize here. And compared to a simplistic grammar-based fuzzer, our type-directed fuzzer was able to generate much larger programs. Moreover, almost none of the other fuzzers' programs type-checked except for truly trivial cases, while all of our fuzzers' programs did. Curiously, there was also relatively little difference in speed between the two approaches to generating solutions, which was reassuring. Neither approach imposes severe overhead. There may be plenty of room to improve performance over our Python prototype, so I will leave the door open to that down the line. We invite you to look over our prototype, which is available at the URL given here or via the QR code. The project was an interesting proof of concept for fuzz testing TVM. We hope to continue to explore this idea in the coming months, and we will soon write an RFC to invite further discussion on the place of fuzzing in TVM development. There are many matters still left open by the prototype, such as handling difficult cases like dynamic shapes and operators like reshape, and we might also consider other issues like generating programs to fulfill constraints or mutating and minimizing programs from bug reports. The biggest problem perhaps will be that of oracles, figuring out how to tell if a generated program had the right or wrong behavior. My collaborators and I hope that you share as much interest in these problems as we do. We thank you very much for your attention, and we look forward to charting the future for fuzzing in TVM, both here at TVMCon and in subsequent RFC discussions. Thank you very much.